Alzheimer's disease is a complex disease. It still lacks a cure and it affects millions of people worldwide, and we certainly still cannot diagnose it early enough. We know that neuroinflammation plays a role in the disease process, but we don't exactly know which role. So it would be interesting to have a look at neuroinflammation and understand where in the disease process it arises. If we could have a look at neuroinflammation at the molecular level, we could understand at what stage in the disease it arises and under which circumstances we start seeing it. And this could give very important information to researchers in order to get closer to a cure. So one of the ways that we can have a look at the molecular level to a condition like neuroinflammation is to make use of radioactive isotopes. Radioactive isotopes and isotopes in general are atoms of the same mass that differ by the number of neutrons. Some isotopes are more stable than others, and those that are less stable decay to more stable ones via the emission of energy in the form of radioactive waves. So one thing that we can do is that if we take a molecule such as the one that you're seeing on the screen, and we make an exact copy of this molecule with a radioactive isotope in some part of the molecule, like for instance this other molecule that you're seeing on the screen, where we have substituted a carbon for a radioactive carbon in the exact same position, which allows us to retain the exact functionalities of the molecule. Then we can have a look at how this molecule interacts with a living organism. We can understand how it's absorbed, how it's distributed, metabolized, how it's excreted from a living organism. And we can literally track it throughout a body. In fact, isotopes like carbon-11 and fluorine-18 are isotopes that emit energy in the form of positrons. And positrons are counterparticles to electrons. Basically, they're just electrons with a positive charge. And in their process of moving in a living organism, they emit these positrons that annihilate, so they meet the electrons in a living organism. And this interaction, which is called an event, releases energy in the form of gamma rays. And we can detect gamma rays in such a precise and quantitative manner that we're able to understand exactly where these events originate in the body, and we're able to build a three-dimensional picture of the movement and the amount of these molecules that is accumulated in the body at a given time. The images that we're hoping to build look a little like this one that you're seeing on the screen. This is an image of a schizophrenic patient infused with a molecule called F-DOPA, which is the molecule you're seeing on the screen. And F-DOPA is a radioactive tracer for dopamine receptors. So an image like the one you saw before, compared to this other one that you're seeing now, this one that you're seeing now is an image of a healthy control patient. The comparison between these two images give us an important information about how dopamine receptors are activated and expressed in a different way between a diseased patient compared to a healthy patient. This is what we're hoping to do also in Alzheimer's disease for neuroinflammation. Once we have a radioactive tracer that is able to probe at the molecular level at neuroinflammation, then we can understand at a certain time point how neuroinflammation is activated. And even more interestingly, we could understand if neuroinflammation could tell us when the disease starts and in which conditions we have to start worrying about the patient developing Alzheimer's disease.